Okay, video on how to differentiate the natural logarithm function. So we've got y equals log of x, and what I'm going to do is I'm going to raise both sides to the power e, and then I'm going to differentiate implicitly. So to get rid of the log, I'm going to say e to the y equals x. That's raising both sides to the power e. Differentiating the left side implicitly, d by dx of e to the y, and I can differentiate this with respect to x. Well, that's just the number 1. I can't differentiate e to the y with x, so I'm going to say it's d to the y of e to the y times by dy by dx. Okay, using the chain rule. This is what implicit differentiation is all about. So the differential of e to the y with respect to y is just e to the y times by dy by dx. That's going to equal the number 1. That tells us then that dy by dx is just 1 over e to the y, but e to the y is x. So therefore that is just 1 over x. So we can see that if y equals log x, then dy by dx is 1 over x. Okay, so that's nice and straightforward. A bit more of a general case. If I have y equals a times the natural log of kx, the dy by dx is just a divided by x. It's not a mistake. K just disappears. This is worth remembering. It's quite easy to remember, but I just want to justify why the k disappears. So what I'm going to do is I'm going to go back to the original function. I'm going to use a log law. I'm going to say y is a times the natural log of k plus the natural log of x. And multiply out the bracket, I get a times log k plus a times log x. And now when I differentiate dy by dx, a is a constant and k is a constant, therefore a log k is just a constant. And we know that when we differentiate a constant, it vanishes. So we just get 0. And then here, we've got a times log x. We've already found that log x differentiates to 1 over x. And differentiation is a linear operation, which means any multiplicative constants will just get carried through. So that is a times 1 over x, which is just a over x. There we go. One more differential I want to look at very quickly is this one. So this is a general base exponential. Y equals a times b to the x. Again, a and b, they are just constants. And the answer of y primed is a times the natural log of b times b to the x. But I want to justify why that is true. Again, this is worth remembering. Right, just times it by log of the base. And if the base is e, then that just becomes the number 1. So what I'm going to do is back to this again, but I'm going to redefine the base of this. So I'm going to say that's a times e to the log b of x. Because e to the power log b is just b. It's just a different way of writing the letter b. Now I can apply a law of exponential up here. So it's a times e to the log of b times x. And now I can see that this is the differential of e to the kx, okay, where k in this case is log b. And we know that that differentiates to a times log b, or a times k, times e to the kx. And then we can reverse the process of e to the log b. A times log b is still there. So we're going to get e to the log b to the power x. And we can see that's just the letter b. So it's a times log b times b to the x. And there we go. Okay, you don't need to know this, but you can just go straight from y to y primed. But that's justifying why that is true.